In this section, we'll finish the restaurant app while skipping some big pieces, such as the implementation of the server. I'm attaching the server project to the module so you would be able to reference and probably run it, but the goal of this course is to teach Codename 1 and not to teach server development. In the next course, we'll cover server development more in depth and touch on some of the work we did for this server. The goal of this module is to finish the app. It's not a goal to create a perfect app, but rather to reach a milestone that we can use. One of the hardest things for developers to do is to finish. We constantly find something new that needs doing, and it becomes harder to reach a point of release. That's why it's crucial to define strict limits and curb your ambition so you can get something into the hands of users. Restricting the feature set to a strict list only works if you maintain discipline and don't embellish the list. Don't add to the entries and don't add new entries. This is the current list I came up with for this app. It includes many missing pieces and some of them are pretty big, but generally it represents the things we need to add or fix. I intend to implement all of these within this module, which is relatively quick. Normally a list like this should take longer to implement. Let's get started with the first item on the agenda, the network layer. And I'll do this by creating an abstraction of the server communication. Despite skipping the server code, most of this code should be pretty clear as we go over it. The DishService implements caching for the dish list. We fetch from the server to make sure the app loads instantly. If we fetch new data, we will show it later, as it's more important that the app loads quickly. Here we check whether cache even exists. This is important for first-time activation. Assuming cache exists, we can just load the data from the cache into the global restaurant object. The cache has the JSON as it was returned from the server, so we can parse it using the standard parsing code. This is convenient for debugging as we can inspect the JSON file in the file system for the simulator and see what's saved locally. The JSON file contains a map object which contains two arrays, dishes and categories. The dishes array contains all the information in a dish, and every entry within this map has the same key value pair as the dish object properties. One of the features of property objects is the ability to populate a property from a map or from JSON directly, and this is exactly the case for which this is useful. The categories are just string names of all the available categories. We could probably just go over the dishes and extract the categories from there. Once we add the categories, we set the Boolean flag indicating the download was finished. This is important as external code might have a listener bound to the property, so it can refresh the UI once the data finished loading. Moving on, we have two separate methods to update the dishes. They are both identical and just use the add to queue and wait or add to queue. The reason we need both is simple. We use add to queue when the app launches, as we want to launch right away and don't want to wait for the data. However, pull to refresh needs to block until the data is here, and in that case we need to use add to queue and wait. The aptly named update dishes from server is the common code for both update methods. It creates a connection request to the dish URL that performs a getHTTP method on the server. The response is parsed mostly, so we can check the timestamp and update the local timestamp. The timestamp trick allows us to send a request with the last received timestamp, and initially we just send 0. This means the server is responsible for updating that value, and if no change was made since the last time the server changed that value, we don't need to receive new data. You will notice that if the data is changed, we save it to cache, then load it from cache later. This is pretty important. We call the loading code from the post response call, which runs on the event dispatch thread. The other callbacks in the connection request occur on a network thread, but the post response call is on the event dispatch thread, and thus it can change the UI or UI related elements. As I mentioned before, we send the timestamp and also an authorization key to the server. The latter is hard-coded for the app, but the former gets updated by the server every time the data changes. Let's move on to the main menu form, where we now fetch dishes from cache if they aren't loaded yet. You will also notice that the pull to refresh call makes use of the update sync method to fetch the updated dishes synchronously. This block represents a very special case of the first invocation, when we have no dishes available and are still waiting. In this case, we place an infinite progress in place and bind the listener to the finished download so we can replace the progress. Notice we aren't concerned about dishes suddenly appearing in the background thread because everything is modified via the event dispatch thread, so we can rely on this being in sync.